Run through a quick discussion with regards to the mandatory experiments and the calculations involved there. So I've got one for the specific latent heat of fusion of ice, as that's when the ice is melting, and then the second one is for the vaporization of water when steam is being added to the calorimeter of water. So these examples have been taken from exam paper questions, very simply from experiment questions, and all the data that's there is taken exactly from the exam paper question. The thing to keep in mind is that when you guys were doing the simulations on the website, it didn't have a mass for the calorimeters in those instances. So we have those values now, and this some people just worked around that and just assumed a mass of a calorimeter. That's fine, it should have worked out without any issues really either, but some of you got a little bit tripped up on that. So have a look at these and see how we go. So you've got all the masses, you've got all the data. I've put little asterisks or stars beside each of the pieces of data that we need for the experiment, or for the calculation I should say. And thing to keep in mind, I would convert to kilos. When we're talking about a delta theta or a change in temperature, it's not going to have a unit value. Or you could talk about it as a Kelvin value, or you can talk about it as a degree Celsius value. It doesn't really matter at the end. They cancel out, so we're only ending up with energy and mass in our unit at the end. So it doesn't really make a difference. You can just take the number as is. The thing to keep in mind here is to think about it in terms of heat lost and heat gained, and they have to be equal. And that's the same for all of these things, or both of these experiments. Okay, so the heat on the left and the heat on the right has to be equal. In this case, we're talking about the fusion of ice, so we're talking about ice melting. So the ice is on the left hand side, that's gaining heat, and the water's on the right hand side, that's losing heat. So they have to be equal to one another, because the ice is getting the heat from the water. So you can imagine we've got a calorimeter full of water, we've got some crushed ice in there. In time, the ice is going to completely melt. It is gaining heat. It's gaining heat. And it's getting heat from the liquid. So the heat is being lost by the liquid and being gained by the ice. So they have to be equal to one another. Hence why we've got an equation. That's what equation means, that we've got something on the left and something on the right are equal, the same as one another. So a little bit of calculation work before you do the proper multiplication and a little bit of algebra involved. Just subtractions, additions to get your masses correct. So the mass of the water, we have to do a subtraction into kilos. The mass of the ice, we have to do a subtraction into kilos. Our change in temperature, now the way to think about this one is, imagine we've got pieces of ice that are at 0 degrees Celsius. What happens to those? It goes through two steps. It goes from being ice at 0 to being water at 0. And then it goes from being water at 0 to being water at 8 Celsius. So the change in temperature overall is that 8 value. Okay, so that's why I've got that there. And again, I've explained that a little bit in that line too. So we've got all of our info there. I like the way to do it here is just to run through exactly what each part is representing. So you can see this is discussing the ice going to water. This is discussing the water increasing in temperature from 0 to 8. This is talking about the copper calorimeter losing temperature, and this is talking about the surrounding water losing temperature. So each part is dealt with specifically and individually, and then we start to combine. So we just pop in our values. Remember these ones, the 4180 there, that's the specific latent heat of water. That is a constant that's given to you in each of these questions. The same for the copper there, is a constant given to you in the question. So you don't have to learn those off. They'll give them to you at the bottom of the problem, and you just need to apply them correctly. So multiplication, 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 we get values there. So you can see I've got the copper is brought down, the water is brought down, and then this one is being brought across. So the water that from the heat gained is going from this side over to the other side of the equals, and that's why it's a minus value now. And finally then we divide it by that 0.0144 to get L on its own, and we have our value. We see our unit is joules per kilogram, and that's all there is to it. Okay, so exact same process for the next one. Again, if you need to have a look at it, pause it, rewind it, go again if needs be. Specific latent heat vaporization of water. So again, we've got all that data given to us, masses and temperatures and so on. You can see I've put them straight away into kilos to make sure there's no confusion, and I pop it straight in to the formula. So again, you've got heat lost on this side because it's the steam losing heat in this case. Okay, so this is lost and this is gained, so it's working the exact same way, just in the opposite direction. We have steam being added to the calorimeter full of water, so the steam is going in here, it's condensing, and it's raising the temperature of the water that was already in the calorimeter. So we have the steam is losing the temperature, and we have the water is gaining the temperature, or the heat energy, if you want to think about it that way. So that's what's happening here. Okay, and again, just the values popped in: kilos, 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 kilos. I've got my specific latent heat, again that's water, a constant given to you in the question, there, and then 390. I'll just rewrite those three for you because they might not be as clear as you can see there. It's 0.0346 multiplied by 390, which is our specific latent heat of copper, and 11.8, which is the change in temperature from 8.2 to 20, I should say, because that heat's going up, because that's the gained side. All right, so we pump all those in, and we get a value of, for each part. You can see this is the part that I popped down here, and it's negative because I brought it to the other side of the equals. That's that one, and that's that one. I'll get rid of those because it makes it a little bit messy. And then the last bit then is just to do your division. So you bring the 0.012 over, it becomes a divide here, and you just divide it straight in, and you get your value for the specific latent heat of vaporization of water. Okay, so again, if you think about it in terms of loss and gain, and they have to be equal to one another, I think it makes it a little bit easier than just think of each body separately. You're talking about the ice, so you're talking about the steam, you're talking about the water once the ice turns into steam, or once the steam turns into water. And then you've got the calorimeter to deal with the copper, and you've got the water that's sitting in the calorimeter before ice is added or before steam is added, depending on the experiment we're talking about. Take your time, read back over them, have a look, see what you think. Thank you.